Okay, today we're looking at correlation. Correlation. All right, so let's say here's this valley right here, and I'm climbing up the side of the valley, got my little geology hammer there, and I'm digging into this layer of rock right there, and I find a fossil. All right? Now, most fossils aren't worth that much because most fossils are pretty common. Sometimes you may find a rare fossil which may be worth something to someone for scientific purposes, or there are some fossils out there that are worth a lot of money too. But let's say that I find a valuable fossil in that layer right there, and I want to find more of them. All right. So besides just digging right, keep on digging that way in that layer to find more of that fossil, I might want to look someplace else for that. And your first instinct is maybe to dig the layer beneath it or the layer above it, but that might not be a good idea because if it's the layer above it, it's going to be from a more recent time period. Layer below it's going to be older. And secondly, that's sandstone right there and that's shale right there. So like shale forms in the deep ocean, sandstone forms near shore. So you're probably not going to have the same type of creatures in the deep ocean as you would near shore. So probably the best place to look for that, for more of those fossils right there, would probably be in this layer over here. All right. Well, what I did there is I was matching rock layers from one location to another location. And when I do that, match rock layers from one location to another location, that's called correlation, and that's what we're looking at today. All right. So we'll look at different specific skills you use to do correlation, some of the problems that can pop up when you try to do correlation, and I'll show you how to do a correlation problem. All right, so first off, one way you could correlate rocks is by walking the outcrop. All right, and what I mean by that is all right, so let's say this is a rock layer right here, and I wanted to see if this rock layer right here was the same as this rock layer right there. Now, if I have a location where there's a rock outcrop, which is where the bedrock's exposed, and it's exposed over a long area, long distance, what I might be able to do is just kind of start in one spot and just kind of follow the rock layer along from one spot to another like that. And then lo and behold, I can see that that's the same layer. All right. Now, walking the outcrop is a very accurate way of correlating rock. It's also not a very practical way because there's not a lot of places where you have rock layers or an outcrop exposed like that over a long distance. So it's something you may be able to do over a short distance, but probably over a long distance, you're not going to be able to do that. So you have to rely on other means to correlate rocks that are farther apart from each other. So very good, very accurate, but not very practical. Next, similar rocks. Rocks intended to be matched based on similar appearance, color, composition. So like this guy right here, he's digging in a shale layer. So first off, what I would look for is another shale layer. All right, well, I have a shale layer here and a shale layer there. So just saying shale layer, that narrows it down, but it hasn't narrowed it down just to one yet. All right. So some other things I can do to narrow it down is I can look at the color. All right. Maybe that's a black shale. That's a black shale, but that's a green shale. So that would kind of tell me, if that one's black and that one's green, that's probably not the same rock layer as that one. So they might have different colors. Or with the sandstone, all right? Sandstone to sandstone, all right? The composition, all right? Now, technically, sandstone is just a particle size. It could be made out of different things. It's just as long as the particles are sand-sized particles. So maybe the sandstone in one location has a different chemical composition from the sandstone in another location. that would mean that they're not the same layer. All right. Now, if I'm just looking at diagrams like this, though, I'm not going to be able to see their color, nor am I going to have a composition. Probably in cases like this, what would be the next best thing to do is look for a sequence. And what I mean by that is look at the layer above it and layer beneath it. Because if you get one right, then the other one should match up too. So going back to this example, this is a shale layer that has a sandstone above it and a limestone beneath it. All right. This one has a limestone above it, sandstone beneath it. So that would mean that this and this are probably not the same layer because the layer above it and the layer beneath it don't match up. If it was the same layer, it would be most likely the layer above it and beneath it would match up well. So like right here, this one, shale, but then if I look at the layer above and beneath it, this has limestone beneath it, sandstone above it, limestone beneath it, sandstone above. So that would probably be the same layer as that one. So it helps to look at like the sequence of rocks as well. All right. Now, something else can help you correlate rocks. Fossils, all right? Fossils give us information about the environment that the rock formed in. So, for example, like maybe fossil A right there, the little circle thing, maybe that's a critter that lived in tropical water. And right here, fossil B, that little cross thing, maybe that's a critter that lived in Arctic water, very cold water. So if that's a tropical water fossil and that's a cold water fossil, that would mean that that's probably not the same layer of rock, right? Because you're not going to find tropical creatures and Arctic creatures in the same type of water. So it probably means they're not the same rock. Now, the best types of fossils for correlating are what we call index fossils. And what makes a good index fossil is a creature that lived in many places or had wide geographic distribution over a short time. Now, what that would look like, well, rock layers are basically time. The more rock layers that something is in, the longer it's been around. So for a critter that lived a short time, that means it's not going to be in very many rock layers. Okay? And I'm looking for something that lived in many places, so we have a wide geographic distribution. So looking at my example right here, all right, so I got 3 fossils, A, B, and C. Only one of those fossils would be a good index fossil. All right, so let's go through these. Well, let's look at fossil A. All right. Now, fossil A, you find it here, you find it there, you find it there. So, wide geographic distribution. However, it's in that layer, that layer, that layer, that layer, that layer, that layer. It's in a whole bunch of different layers. And what that would suggest is that it's lived for a long period of time. So if I find something that's in a whole bunch of locations for a long period of time, that really doesn't help me at all, because that means that, like, you know, you could find that fossil anywhere. So it doesn't really help you correlate a specific rock layer. All right. So that's why A is not a good fossil, index fossil. All right, fossil B, that guy right there. All right. Now for that one, well, it's only in the one rock layer, which is good because that means it was only around for a short amount of time. However, I only see it in that one location. So that means it does not have a wide geographic distribution. It's just found in that one location. So I'm not likely to find that anywhere else because it's only in that one spot. All right. The best index fossil of those 3 would be fossil C, because fossil C is in only one layer. All right, so that means it lived for a short amount of time, and it's in multiple locations, so it had a wider geographic distribution. All right. So fossil C would be the best index fossil there. All right, something else to help correlate rocks is volcanic ash deposits. All right. Now, there's different types of volcanoes. Normally, when people think of volcanoes, they think of the ones like in Hawaii, where you have the red lava comes out and kind of flows down the side. Those are the ones that you find in the middle of the ocean. The ones that form on the continents are a lot more explosive than that. And the reason being it's a different type of magma. But anyway, so the ones that happen on the continent, there's lava with them as well, but usually they explode a lot and they spew a lot of ash up into the air. Now, a volcanic eruption is a fairly short event time-wise. A volcano may erupt for a few days or something like that. So geologically speaking, it's a very short amount of time. But the ash that spews up there is blown over a large area. And that ash will eventually settle down and end up getting in the soil and becoming part of the rock. So you have something that was caused by an event that was very short-lived, but the remains of it got spread out over a large area. The ash went up and then the winds blew it around and then it finally settled down. So volcanic ash deposits are very, very useful for trying to correlate rocks. Right? It's rapidly deposited over a large area, which is a similar properties to a good index fossil, right? Volcanic ash, rapidly deposited. If something's rapidly deposited, it was deposited over a short time. Volcanic ash deposits happen over a large area. Index fossils are the main places, so it's basically a large area. So what makes something a good index fossil is also similar characteristics to what makes volcanic ash useful to correlate rocks. All right, now, some of the things that can make correlating rocks a little on the tricky side. Right? One thing is unconformities. All right? What an unconformity means is that you have rocks that are missing because of erosion. There was stuff there, but erosion has taken it and made it disappear. So I have missing information. On diagrams, it's usually kind of represented by kind of a squiggly line. So let's say I want to correlate these guys right here. All right? So this, fairly simple. This, I look sandstone, sandstone, limestone above, shale beneath, limestone above, shale beneath. So that those two correlate like that. All right. Then I look over here, and this one correlate, but that's not the same as that one right there. So you might think, oh no, I can't do any correlation. Well, here's the squiggly line right there. That means that there's erosion. So there was something here that eroded away, and then that shale got deposited on it sometime later. All right. So just because I don't see the limestone here doesn't mean that these other things don't match up, because there probably was limestone there at one point, but the unconformity tells me that that eroded away and then something else new got deposited on top of it. All right. So unconformities can make trying to correlate rocks a little bit tricky. Something else that can make rocks or correlating rocks a little tricky, problem with correlation, some rock layers may not appear in different areas. And what I mean by that is, let's say I'm trying to correlate these guys right here. All right. So I look and I see, all right, so limestone with shale beneath it, shale above it, limestone, shale beneath it, shale above it. So that kind of correlates like that. That goes like that. That goes like that. All right, so now I'm trying to match over there. I'm like, well, I can see these guys going like this. And I can see this going like that. But then I'm missing a layer in the middle there. All right. This is all shale, and that's got shale, limestone shale. All right. Well, sometimes if you're trying to correlate rocks, the closer they are together, the more likely they're going to be similar. The farther apart they get, the less likely they're going to be, very similar to each other. They get different farther out apart they get. And the reason being is, if this one and this one are, if this one and this one are 5 miles apart, then it's going to be very similar. If this one and this one are 100 miles apart, well, what's going on here and what's going on 100 miles away, could be significantly different. And what likely happened here is that the conditions that form that limestone there and there, and you can already see that layer of limestone right there is getting thinner, is that just didn't happen over here. All right, so as we went from those two, that layer of limestone looks like it probably just kind of pinched out. So it was thicker and then got thinner and thinner and thinner, and this kind of petered out. So then the rest of this matches up fine. It's just this layer here, the conditions that were creating this limestone over here just didn't exist over there. So sometimes you could have a layer just kind of peter out like that. All right, so do another correlation problem. One that's bottom of the notes. All right, so let's say I want to do a correlation of these guys right here. All right. Now, I'm looking on here. Just one second. All right, so I want to correlate them, and then what I also want to do is figure out which fossil is the best index fossil. So I want to pick a layer. So let's say I pick this layer right here. I got sandstone. So I want to correlate the sandstone to this section over here. Now, what I'm looking for is a sandstone that has a limestone above it, limestone beneath it. So I look at this one, for example. It's got a limestone beneath it, but it's got a shale above it. So that would mean that this one and this one are probably not the same sandstone. How about this one and this one? All right. Well, again, limestone above, limestone beneath. I come to there. That's got a shale above it. So since these guys don't match up, that probably means that that one and that one aren't the same layer. So this one, all right, limestone above, limestone beneath. Limestone above, limestone beneath. So it looks like this one is that rock layer right there. Then if I get that one right, the other ones should probably fall into place. That. Like that. All right. Now I noticed that with this, I don't see any shale on top of this one here, but there's a squiggly line. That means erosion took place. So there was probably shale there at one time, but eroded away. Now for this one here, again, I'm looking for a sandstone. It's got limestone above, limestone beneath, limestone below, limestone below, limestone above. And that goes there. And once that one's hooked up, if I did it right, these other ones should match up as well. That goes there. That goes there. That goes there. All right. Same thing. I don't have the shale right there, but again, there's a squiggly line. That means there was stuff there that eroded away. All right, so there is my correlation. Notice my correlation lines run somewhat parallel to each other. If you do a correlation and they crisscross, you probably did something wrong. All right. Now, as far as my fossils go, I got fossil A and fossil B. Only one of those are a good index fossil. And remember, a good index fossil is one that where they lived in a lot of places, but only for a short amount of time. So I'm looking at these guys, and I see with fossil A, it's there, it's down there, it's in the middle. Fossil A is kind of all over the place. It's in all three locations, which is good, but time-wise, it's in the bottom layer and the top layer. So that means it was around for a long period of time. So that's not a very good index fossil if it's been around for a long period of time. I look at fossil B, and fossil B is right there, right there, right there. It's in all the locations, which is good. And the other thing about it is it's only in that one layer. That means it only existed for a short amount of time. So it was in a lot of places for a short amount of time. So fossil B is the better index fossil. Now, another type of question you might get with these guys here, they might say something like, which column has the oldest rock layer in it? All right. So if I got a question like that, what I would be looking for is which column would have the layer that kind of works out to be the farthest one down. So like with this one, here's the oldest rock layer there, but it works out to be that right there. The oldest rock layer there is that one there. So the oldest overall one would be this layer right here. So this would be right here would be the oldest one. And if someone said which column had the youngest rock layer, well again, there's the youngest one there, is the second highest up there. Here's the youngest one there, the second highest one up there. So this layer here is the one that's highest up. So overall, that layer would be the youngest layer. All right, so that's how you do correlations. And I always like them because they're kind of like puzzles.